Alright, so in this video we're going to do a little bit more with vectors. Specifically, we're going to learn kind of the two fundamental operations of vectors, and they're addition and scalar multiplication. So the basic idea here is just like if you had a pair of numbers, you can do operations with them. So like if you had the numbers 3 and 6, you could add them together and get 9, or you could multiply them and get 18. Well, you can also do operations with vectors. And the two most fundamental operations that you do with vectors are addition and scalar multiplication. So the idea with addition is just, suppose you have two different vectors and you want to add them together. So pictured is a vector whose component form is 4, 4, and a second vector whose component form is 0, -2. If you want to add these vectors together, and we don't quite understand what it means to add vectors at this point, but if you were just playing along and somebody gave you two and said add them together, well, think about how you would hope this is defined. What would make life as easy as possible? The answer for me anyways would be component addition, meaning that when I took these two vectors and added them together, I got a third vector, and the first component of this new vector would just be the sum of the first components in the two vectors I was adding together. So this 4 plus this 0 would give me this 4. Similarly, the second component of this new vector would be the sum of the second component of my first vector and the second component of my second vector. So 4 plus -2, or 2. And the good news is that's exactly how vector addition is defined. You just add the components. Geometrically, all we're really doing is plotting our first vector and then taking the second vector, and instead of picturing it with its initial point at the origin, we draw it with the initial point at the terminal point of the first vector. What I'm saying is take this vector right here and start it up here. To sum two vectors, you kind of just sketch them tip to tail. So the second vector starts where the first vector ends. And just like addition of numbers is commutative, 3 plus 6 is the same as 6 plus 3, addition of vectors is commutative. So 0, -2 plus 4, 4 is the same as 4, 4 plus 0, -2. Geometrically, we can think about this as sketching the red vector, except starting at the end of the blue vector. And noting that either way, we end up at the same point, pictured in green out here. And maybe you're like, wait a minute, that's a point. I thought the sum of two vectors should be a vector. Yeah, you're totally right. Pictured is just the point 4, 2, not the vector 4, 2. The vector 4, 2 would be this arrow in green that if I oriented it to start at the origin here, it would end up at the point 4, 2. Why would you care about this? Well, I guess I can give you a somewhat real world situation. One application of vectors is to represent forces. So pretend I go out into my backyard on a windy day. This red vector could represent the force of the wind. So the wind is blowing in a northeast direction, and the speed of the wind is represented by the length of this arrow in red. Using the Pythagorean theorem and the fact that this point is at 4, 4, we could calculate the length of this arrow in red to be the square root of 32, or 4 times the square root of 2. But now pretend there's another force. I don't know, a giant fan maybe. My son's got this fan and he set it up so that it's blowing due south. The force of the fan is represented by the blue vector. The fan is not quite as powerful as the wind, so the blue vector is not quite as long as the red vector. The blue vector only has magnitude 2. Now pretend that for some reason, I don't know why, I want to drop a piece of paper and have it land right at my feet. Well, that's going to be tricky because if I drop a piece of paper, the wind is going to blow it northeast and my son's fan is going to blow it south, and it's not going to land right at my feet. But what I could do is kind of throw the paper a little bit in some direction so that it cancels out the forces of the wind and the fan and lands right at my feet. How would I throw it? Well, it's complicated because I have to account for both the wind and the fan. Fortunately, I can combine those two forces into a single force by just adding them together. The force of the wind is pictured in red, the force of the fan is pictured in blue, and both of those forces combined is pictured in green. So if I wanted the piece of paper to fall right at my feet, I'd have to provide my own force in the opposite direction of this force to cancel out the combined forces of the wind and the fan. If I wanted to represent this all mathematically, I could say that the force of the wind plus the force of the fan plus this third force that I'm going to create when I throw the piece of paper in a given direction. Maybe I'll represent that vector x, y. And since I want the paper to fall right at my feet, I want all of these forces to cancel each other out and end up with a vector of 0, 0. Well, we already know that the sum of these first two vectors is just 4, 2, either algebraically because we add vectors component-wise, or geometrically because we can think about the two forces combined as creating this vector shown in green. So really the question becomes, what new vector would I need to create here so that when I added that vector to these combined forces, I ended up with a net force of 0? Well, because we now know how vector addition works, it's easy enough to see that the x would have to be -4 to create this 0, and the y would have to be -2. The takeaway is that addition of vectors works just like you'd kind of hope it would work, and just like you'd probably guess it would work if I didn't tell you how it worked. All you got to do to add vectors is add them component-wise. A book will tell you that if we have these two arbitrary vectors, a, b, and c, d, their sum can be written in its component form as a plus c, comma, b plus d. But that looks a lot more complicated than it needs to be. As long as you understand how 4 plus 0, negative 2 sums to 4, comma 2, you're good. And more good news, scalar multiplication isn't much more complicated than addition. There are a few little subtleties though, so you got to be a little bit careful. With addition, we're adding together two vectors. With scalar multiplication, we're not multiplying two vectors. We're taking one vector and multiplying it by a number. In other words, a scalar. So for example, the scalar 3 times the vector 1, negative 2. Written differently, I could define my vector u to be equal to 1, negative 2. And then I could ask about what 3u is equal to. Well, just like addition of vectors, scalar multiplication of vectors works in probably how you would like it to work if it was up to you to choose how it worked in the first place. 3 times this vector 1, negative 2 is just going to be equal to 3, negative 6. All you do is take the scalar and apply it to each of the different components of the vector. In other words, multiply the 1 and the negative 2 by the 3. So if my vector u is 1, negative 2, 3u is just 3, negative 6. The way you could think about it is, here's my original vector with components 1, negative 2, oriented so that it starts at the origin and ends up down here with an x-coordinate of 1 and a y-coordinate of negative 2. If you want, it's my son's fan, except he's pointing it in a slightly different direction and it's a little bit stronger than it was above up here. Well, what if my son doesn't just have one fan, but instead he has 3 fans? They're all of equal strength and they're all pointed in the same direction. And I want to think about the combined force of these 3 fans. Well, that force could be represented by a vector very similar to this vector shown in blue. It would just be longer because it would be stronger. In fact, it should be 3 times as long. So instead of ending at 1, negative 2, it should end at 3, negative 6. And that's exactly what it does. Scalar multiplication just kind of stretches this vector by a factor of 3. And just like we can scale this vector u by a factor of 3, we could scale this vector u by a factor of, negative 2. What would that do? Well, what would you think it would do? I mean, it would be kind of nice if I could use the same rules that I used up here, where I just took the scalar, formerly 3, now negative 2, and multiplied that by each of the components of u individually. That's exactly what you do. Negative 2 times positive 1 gives me negative 2. Negative 2 times negative 2 gives me positive 4. If I wanted to scale my vector u by a negative 2, the resulting vector would have components negative 2, 4. Loosely speaking, we'd have a new vector that's twice as big as the one in blue, but points in the opposite direction. That's it. Addition and scalar multiplication of vectors is fairly straightforward, but we don't want to just gloss over it because these are new objects, and when we have new objects, we have to be really careful in terms of how we handle them. Fortunately, the way we handle them is just the most intuitive and natural way that you can imagine. To see if this all makes sense, let me do an example real quick. Suppose I have these 3 different vectors, u, v, and w, and I'm defining them in their component form so that u is 1, negative 2, v is 3, 5, and w is negative 1, negative 3. What if I asked you to evaluate 2u minus 3v plus 4w? Well, if u, v, and w were all numbers, this would be a really easy question. We'd first multiply each of the individual terms and then add and subtract those products. But they're not numbers, they're vectors. This new kind of strange object that we're still wrapping our head around. But fortunately, the way things work out is pretty easy. I think it helps to rewrite u, v, and w in their component form as is listed above. So things would look like this. Just like with real numbers, how we multiply before we add in our order of operations, with vectors, we want to apply scalar multiplication before we apply addition. So I'll think about the product of this scalar 2 and this vector 1, negative 2. As we saw earlier, scalars just hit each component individually. So the product of this scalar 2 and this vector 1, negative 2 would be 2, comma, negative 4. The product of a scalar and a vector is a vector. And then we get to the product of this scalar and our second vector, and maybe you're a little bit nervous. You're like, wait a minute, you defined vector addition, but not vector subtraction. What am I going to do here? Well, there is no vector subtraction. It's just vector addition with a negative scalar out in front. You could argue that this shouldn't be written this way. It should say plus negative 3 and then the vector 3, comma 5. But having a plus and a negative next to each other looks weird mathematically, so we just accept that that's what they mean when it's written this way. We don't subtract vectors, we add them. And if it looks like we're subtracting them, really we're just adding a different vector that needs to be multiplied by the negative scalar that's out in front of it. All I'm saying is take the negative 3 and distribute that to the two components of this vector to get -9, -15. Finally, the scalar of 4 times the vector of -1, -3 results in a new vector whose components are -4, -12. And now I just have a sum of these three different vectors. So if you were being really careful, maybe you'd first add these two vectors, because really we've only defined how to add two vectors, not three vectors. But the sum of these two vectors is itself a vector, and we could take that resulting vector and add to it this new vector. But maybe you can quickly convince yourself that that would give us the exact same result as we'd get if we added the first component of all three vectors, so 2 plus -9 plus -4, which gives me -11, and then added the second components of those three different vectors, -4 plus -15 plus -12, to get -31. One more example before I call this video good. There's two special vectors that get special names, typically the letters I and J. Typically, the way the vector I is defined is to be 1, 0. And the way the vector j is defined is to be the vector 0, 1. And with those definitions, somebody might ask you about the vector, I don't know, 3i minus maybe 5j. Sure. Well, let's see what's going on here. Instead of writing I can write that vector in its component form, so 1, 0. And then instead of writing j, if I wrote that in its component form, I'd have a 0, 1. Much like we saw above, we're first going to apply the scalars to the vectors before we add the vectors together. So if I apply this scalar of 3 to my first vector I would get the vector 3, 0. And if I apply this scalar -5 to my vector j, I would get the vector 0, -5. Now that I have two vectors, I can add them together, 3, 0 and 0, -5. Well, the first component is just 3 plus 0, or 3. And the second component is 0 plus -5, so -5. What I'm saying is with I and j defined this way, 3i minus 5j would just be this vector 3, -5. And you're like, yeah, I could have gotten that right from the start, right? This 3 just ends up being this 3, and this -5 just ends up being this -5. Yeah, that's totally right. If we define I and j this way, then even though this kind of looks like a question that needs to be evaluated, 3i minus 5j, we can kind of see how that immediately gives us this vector 3, -5. In fact, it's so immediate that sometimes this isn't even thought of as a question. This is kind of thought of as an answer. If I have this vector 3, -5, one way I could represent it is 3i minus 5j. Going back to the very first video that I made on vectors, we had this vector u, and I said that either 2i plus 4j or 2, 4 can be used as the component form of the vector. Maybe now we can see how these are really the same thing. This is 2 times the unit vector 1, 0, and this is 4 times the unit vector 0, 1. Since I has a 1 as its first component and a 0 as the second component, whatever the scalar is that I'm multiplying I by will become the new first component, and the second component will always stay at 0. Similarly, the scalar that I multiply j by will completely determine the second component. The first component will always stay with 0. Here's the picture. If I can get this picture to make sense, I can end this video. The vector I, which written in component form is 1, 0, is this little red arrow here, pointing 1 unit to the right. The vector j, written in its component form 0, 1, is this vector right here, the arrow pointing up 1 unit. If I wanted to think about the vector 3, -5, in other words 3i minus 5j, I could think about it just as this arrow pictured in green, or as 3 copies of this arrow pictured in red, and informally speaking, 5 copies of this vector pictured in blue with its orientation reversed, all added together. Why would you ever want to think about it the red and blue way instead of the green way? Well, it really depends on the application, but sometimes for a given vector, we really just want to think about its components. Like if you're standing on the edge of a cliff and you really don't want to fall over this cliff, and it's a windy day, and the force of the wind can be modeled by this vector here, really all you're concerned with is the component of the wind that's blowing you over the cliff, this 3. Not the component of the wind that's blowing you further down along the cliff, this 5. Anyways, if that makes any sense, great. But really the big takeaway for this video is understanding the two fundamental operations dealing with vectors. Vector addition, where you take two vectors and add them together, and scalar multiplication, where you take a number, aka a scalar, and you multiply that by a vector and produce a new vector. If you have the two of those down, you're in good shape.